Hello, my name is Melanie Chen, and I will be presenting my project on the development of an image segmentation algorithm using geometry, curve evolution, and user interaction. Image segmentation is the process of separating a foreground from a background. It is used in many areas, including photo/video editing softwares and medical settings, in order to isolate tumors, organs, etc. from medical scans. Medical image segmentation algorithms are created to save time from having humans manually segment images, and these algorithms must be able to segment these objects properly and accurately. One of the current approaches being used is machine learning. Machine learning algorithms involve training a machine by passing through data until it learns how to complete a task. Machine learning is often used to segment medical imagery because it does not require a human's assistance. However, there are a few cons to this approach. First, the algorithms require a large amount of data and resources to train the machine to segment images. Next, these algorithms are limited to the types of images that it is trained with. If a machine is trained with CT scans, it will only be able to segment these types of images. Because of their lack of range and use, this makes these approaches much less versatile compared to other alternatives. Along with this, these approaches are time-consuming since they require a training period. Lastly, these approaches are often prone to computer error since it is completely automated and computers are not able to perceive images the same way humans do. Despite these cons, there are alternatives to machine learning approaches. For example, curve evolution. Curve evolution algorithms create a curve on top of an image and gradually evolve the curve based on image data until it is able to detect images and successfully segment the image. Some pros to this approach is that it is very versatile. Curves are able to adapt to any shape, so the algorithms are not limited to just one type of image. The second advantage is speed. Curve evolution does not require a training period, so they can be used to get a result quickly. Finally, user interaction can be incorporated into these approaches to reduce error. By combining automated and user input, a computer mistake is able to be resolved by a human who can affect the curve, forcing it towards the right direction. The research completed used qualitative data, and the data analysis was done visually. In this project, I decided not to do a quantitative analysis because I wanted to complete an initial visual pilot analysis before undertaking a study with quantitative analysis. I intend to test hypotheses in the future using quantitative data and a statistical analysis. However, this research was meant to generate a hypothesis rather than test a hypothesis. In this project, I will be comparing the results of a curve evolution algorithm with user input and one without user input to determine which is more accurate. The objectives of this project were the following: to integrate curve evolution and implement mean intensity image segmentation, which is the mechanism in which the curve will use to evolve, to combine control, geometric partial differential equations, and user interaction to achieve the most accurate algorithm, to develop an algorithm using MATLAB, and to compare the results between an algorithm using user input and one without. The assumptions made in this project were that all materials were configured correctly and accurately, and that multiple algorithm runs with the same input image would result in the same final segmentation. The equipment required for this project was a computer, MATLAB R2019 software, and test images. The project was conducted at the Department of Bioinformatics at Stony Brook University in New York. Now, how the algorithm works. The process can be broken down into three main components: initialization, curve evolution, and user interaction. First, the algorithm creates a rectangular binary mask of the inputted image. This mask has the same dimensions as the input image and creates a rectangle on top of the image that only contains 0 and 1 pixel values, making it black and white. Next, an image and ideal level set are created. A level set is similar to a topographic map in that both contain 3 so-called dimensions. Each point on a topographic map has an x and y coordinate as well as an altitude. Each point on a level set also has 3 pieces of info. A level set is made up of Euclidean distances that measure the distance from each pixel value to the closest pixel with a value of 0. In this image of the level set, the orange line indicates all pixels with a value of 0. The other pixels in the set are the Euclidean distances from each individual pixel to the nearest pixel with a 0 value. 2 bands will also be created on the image and ideal level set. A band is made up of a small range of values in the level set, and this band will represent the evolving curve. Next, the algorithm uses a simple piecewise function called the h function to change the signs of each pixel value so that those inside the curve are positive and those outside are negative. The separation in this image is indicated by the orange lines. The last step of the initialization process is to create colored masks of the image and calculate the mean intensity values inside and outside the band of these colored masks. A colored mask is made by multiplying the binary mask by the input image so that only certain areas of the colored mask will have RGB pixel values that range from 0 to 255 instead of just 0 and 1. The algorithm uses these intensity values to evolve the band by comparing them during each iteration. The next component is curve evolution. The algorithm uses the Yazzie equation to determine the vector/direction in which each point on the band will go towards. This equation describes the gradient descent using the original image and the outer and inner mean intensity values. As the algorithm runs, it will continue to collect data from the image to evolve the curve. The last component of the algorithm is the user interaction component. During each iteration, two types of error will be calculated. The user error is the error between the user input and the ideal level set, while the machine error is the error between the image level set and the ideal level set. As the curve evolves, both errors change due to a change in image data. As the curves of the image level set and the ideal level set evolve, the ideal is directly influenced by the user interaction, causing it to follow in the path of the marks created by the user. As the ideal curve moves, the image level set is then forced to move in the same direction. The goal of the algorithm is to minimize both types of error in order to achieve the best segmentation. Once both types of error are constant for 1,000 iterations, it is concluded that the algorithm has reached an edge and the algorithm stops running. The algorithm was tested by inputting various images and studying the curve evolution and accuracy of each segmentation. The segmentation result was then compared to the ideal segmentation visually by eye. The images on the right display snapshots of a few points in time while the algorithm is running. Column A indicates the curve evolution on the original input image. Column B shows the image level set with a contour as well as the image band. Column C shows the ideal level set with a contour and a band. And finally, column D shows the accumulated user interaction. The yellow and orange marks indicated in column D are the lines being drawn by the user, which, as you can see, force the bands to move in that direction in order to segment this other object in the foreground. The same test image was used in a curve evolution algorithm that used user interaction and one that did not use user interaction to see which would result in a more accurate segmentation of the original image. As you can see below, the algorithm using curve evolution with no user interaction was not able to segment both subjects in the image, unlike the other algorithm. The algorithm using user interaction was unable to segment both foreground objects in the image. The algorithm using curve evolution and user interaction demonstrated being able to successfully segment complicated images that would have been difficult for a fully automated algorithm. The analysis was not able to be completed quantitatively yet. However, the future goal is to analyze this data using some sort of statistical analysis. Because I was not able to form a quantitative analysis, I am not able to accept or reject a null hypothesis, but I am able to make a conclusion based on the qualitative data taken by eye. Ultimately, an algorithm was created using MATLAB as a successful, accurate alternative to machine learning approaches. The algorithm is able to be used with many different types of images and can be used on the fly, which are settings in which a segmentation is required at that moment. In these on-the-fly scenarios, machine learning approaches are not ideal because of the resources and time they require. The algorithm was tested with many different types of images and compared with the results of an algorithm that did not incorporate user interaction. This comparison showed that the presence of user input in the process resulted in a better, more accurate segmentation. Plans for future research. In the future, I would like to test hypotheses involving the accuracy of these algorithms and test them using a statistical analysis. For example, comparing the segmentation result versus a human segmentation of the image to test how accurate the algorithm is. I would also like to implement this algorithm into a mobile app to make it more accessible for physicians. Finally, I would like to be able to gain access to real medical imaging for a more realistic application of the algorithm and to be able to optimize the accuracy of this algorithm. These points above just state my future endeavors. However, this project really did open up my eyes to a professional research experience, which I have learned so much from. Thank you for listening and supporting my passion for research.